Today we are moving on to our new topic, which is polar coordinates. In your textbook, this is sections 10.6 through 10.8. We're not going to be covering everything in 10.6 through 10.8. We're going to get a pretty good overview of what the important concepts are. We're going to more or less follow the 10.6, 10.7, 10.8, but not exactly. All right, so as a quick pre-example before we get into this PowerPoint, when you are dealing in rectangular coordinates, which is what your experience has been so far, if you wanted to locate a point, you would do so by indicating how many units right or left off of the origin are you traveling, then how many units up, down off of that particular value are you traveling in order to reach that particular point. What's going to happen with polar coordinates, instead of locating that point right there with an X and a Y, we're going to locate it with an R and a theta. Okay, the R and the theta are going to have a similar type of meaning, lots of similarities between this stuff and what we learned when we first started talking about angles in standard position leading into the unit circle. R is going to be how far that distance is from the origin to the point in question. And the theta is going to be how many degrees or radians are we rotating up to that particular line that gives us the distance from here to here. So instead of an XY, it's going to be an R theta. Lots of similarities between what we're doing here and what we did with learning about angles in standard position, but there are going to be a couple of differences. All right, now on to the PowerPoint at hand. To form the polar coordinate system in the plane, fix a point O called the pole or the origin, and construct from O an initial ray called the polar axis as shown below. So what happens here is what was the origin in a rectangular coordinate system is sometimes still called the origin now, but it's also referred to or could be referred to as the pole. Okay, the positive x-axis in our rectangular days are going to be what's known as our polar axis. It's what we're measuring that angle off of. Then each point P in the plane can be assigned the polar coordinates R theta as follows. R is the directed distance from O to P. Theta is the directed angle counterclockwise from the polar axis to segment OP. So that corresponds to what I did here, except with a little bit different vocabulary that's more commonly used with this particular topic. All right, so first thing we're going to look at is, well, how do you go back and forth between the two coordinate systems? Well, what if you have something that's in rectangular and you want it in polar? What happens if you have something in polar and you want it in rectangular? Okay, so what's associated with that? So, leading up to those ideas, the point R theta, 2 pi over 3, lies 2 units from the pole on the terminal side of the angle. Theta is equal to pi over 3. So this is your typical looking blank coordinates for polar coordinates, or blank graph rather. So the 2 refers to we're 2 units that way. The pi over 3 refers to pi over 3 rotation from the polar axis, which was formerly known as the x-axis, up to that terminal side. In rectangular coordinates, each point xy has a unique representation. This is not true for polar coordinates. The coordinates r theta and r theta plus 2 pi represent the same point. So if we were to rotate around another full circle, that would be another way of locating that same point. So 2 pi over 3 and 2 pi over 3 plus 2 pi, locate that same point right there. Okay, you could also subtract 2 pi to go around that way. You could add multiples of 2 pi, you can subtract multiples of 2 pi. So there are an infinite number of ways in polar coordinates you can name that point right there. Now back in our introduction to standard position days, r was always positive. Now, as I mentioned earlier, there are lots of similarities between what we're doing here and what we saw back in, I think it's section 4.3 in the textbook, somewhere in that neighborhood. But there's also some key differences. Okay, one of those key differences is r can now be negative. What happens is r is negative, basically it shoots this arrow the other way. So a negative r means it's going down this way instead of up that way. So to get back to that same location, you'd be adding or subtracting pi. And it doesn't matter what you do, because whether you add pi or subtract pi, it takes you to the same place. So another way that we could represent that point 2,3 in polar coordinates is we can make it negative 2 and then pi over 3 plus pi. Or you could do pi over 3 minus pi. All take you to the same place. Okay, we're not going to make it a key emphasis for what we do in this class of all the different ways you can name that point using polar coordinates, but you need to be aware it exists, because sometimes you get some things that don't quite fit together when you're solving a problem, and you need to tweak them to compensate, to make it look better, so to speak, by knowing these facts right here. The most important thing here is how do you graph that? A secondary thing is there's more than one way to name that particular point that'll mark that same location on the coordinate plane. It's not going to be an emphasis, but it does sneak in every once in a while, and you have to be aware of it. Okay. Now, building up further to that idea of going back and forth between the two types of coordinate systems. To establish the relationship between polar and rectangular coordinates, let the polar axis coincide with the positive x-axis. We've already mentioned that. And the pole with the origin. We've already mentioned that, as shown in the figure. So we want to be able to go back and forth between xy and r theta. So one of the relationships here is that r squared is equal to x squared plus y squared. And typically, we would like it, most of the time it is going to be positive. It can be negative, refer back to the previous slide, adjust as necessary. All right, assuming we're dealing with the r as positive, this stuff kicks in from back in the chapter 4 days. We know that the tangent of an angle is y over x. We know that the cosine is x over r. We know sine is y over r. Now, it's still going to be true with some minor tweaking for the r less than 0. Again, it's not the main thing. We're just going to have to use that every once in a while, and as it becomes important, we'll address it. So, in our chapter 4 days, these three guys were true. This one, we're pretty much going to leave it alone in our chapter 10 applications. For these two, it's much more convenient to multiply both sides by r. Rather than thinking about cosine of theta as x over r, it's better to think about it as x is equal to r cosine and y is equal to r sine. So these two tweaked come to here. This is as is, that x squared plus y squared thing from the previous slide kind of gives us our block of stuff we're working off of. Knowing this little block of stuff will get the job done for any conversions. So, convert root 3 pi over 6 to rectangular coordinates. So that's an r, that's a theta. If we're starting with rectangular coordinates, I'm sorry, starting with, that's not rectangular, starting with polar and converting to rectangular, we can just take those two things and plug them into each one of those guys right there. So we know x is r cosine of theta, root 3 times the cosine of pi over 6, order of operations. Y is r sine of theta, root 3, sine of pi over 6, evaluate, plug them in. So in regular xy or rectangular coordinates, the point root 3 pi over 6 corresponds to 3 halves root 3 over 2. Okay, what if we're going in reverse? Always helpful to plot the point. Well, no matter what you're doing, if time permits and you're plottable, that's a good strategy. If we're going from rectangular to polar, we're going to know xy. So from xy, we can get the r. And then from the tangent of theta being y over x, just putting that in inverse form, we can get the theta by the inverse tangent of y over x. Now sometimes, again, this may not quite work out to be as coming together as you would like. If necessary to choose the theta that lies in the same quadrant as xy. That's where we're going to have to tweak a little bit sometimes with that negative r and everything else. Again, this is not going to be a big emphasis, but it's something you should be aware of. All right, now sometimes kind of common sense rules. There's not really a necessity to use any formulas, anything other than just basic observational skills. So say you had the point 0, 3 in rectangular coordinates, and you want to convert that to r theta. Well, you can get r simply by realizing you're 3 units straight up from the pole. There's your r. Well, how many radians do we have from there to there? It's pi over 2. There's no formula necessary. There's no reason to make it any more complicated than it needs to be. There are some of these that are simply just look at it from pure observation, what is the correct answer. Okay, for the next two, we'll take more of a formula-driven approach, not necessarily just by observation. And I think it might be easier to kind of show some graphs a little bit more here. So for part B, we have the rectangular point 2, negative 2. So 2, negative 2 is down here. That's our xy. We want to express that as an r theta. So we need an r value. So we got 2 squared plus 2 squared equals what squared? And you can include or uninclude the sign, it really doesn't matter. That gives us 2 root 2 for an r value. And then we got the tangent of theta is equal to y over x. So that's the tangent of theta is equal to negative 2 over 2, where theta is the inverse tangent of negative 1, and that's negative pi over 4. Oop, pi over 4. So that would be one way that we could express that point in polar form. What if, say, for some reason you didn't want your theta to be a negative angle? And then you could come around this way, and instead of negative pi over 4, rewrite it as 7 pi over 4. And here, it gives you a couple other options in terms of how it could look. I'm not going to emphasize that. I think one of those two would be the way that you would choose to express that. Fold this over here. Okay, so for this one, negative 3, 1, I'm not even going to try to scale a negative 3. Where would that be? So roughly know that's in the second quadrant here. So to get the r, x squared plus y squared equals r squared. The radius turns out to be 2. Then we need to do the inverse tangent of y over x, which is the inverse tangent after you clean it up to make it more like what you're used to seeing. Negative root 3 over 3. Now the calculator is going to say negative pi over 6. So that's actually down here going this way. So what we need is something that's completely opposite of it over there. So what angle is over there on the opposite side? Or another way to think about it, probably the most consistent with what we did back in chapter 4, would have to have the same reference angle as negative pi over 6. So this certainly does not match the picture. So what angle would make sense in the picture? To use the 5 pi over 6. And again, there's an infinite number of ways that you could be flip-flopping around here in terms of writing that in polar coordinates. That would be the most obvious one. I suppose if you wanted to stick with that negative pi over 6, we could do negative 2, negative pi over 6 would get you to the same location. All right, next thing we're going to look at. 2 points are specified using polar coordinates. Find the distance between the points. In terms of actually finding the distance between the points, this type of question is not in your textbook. So for those of you that look to see where does everything line up with what we do in the textbook, this is not in here. It involves stuff that we've talked about. It's good practice of other things, but that question as is isn't in the textbook. All right, so let's locate these. 4, 3 pi over 2 is going to be down here. That's a 3 pi over 2 revolution coming this way, 4 units from the pole. Okay, 4 pi is right there. And what they're asking us to do is to find that distance. How far is it from there to there? Well, the easiest way to do this one right here is to recognize that we can box this in to form a right triangle. That's 4. This is 4. The two axes are perpendicular to each other. So you can do a squared plus b squared equals c squared. Recognize it as a 45, 45, 90, whichever your preference is. And 4 root 2 is going to be that distance. Okay, next question. Same type here. 3, 2 pi over 3. So 2 pi over 3, 3 units. That will be right here. Okay, 4 pi over 6. That will be right there. And they're asking us, what's that distance from there to there? Well, we get another problem where we can box it in to form a right triangle just like that. So we know that this leg is 3. This leg is 4. And just to verify that that is a right angle, we can think about it in degrees. Pi over 6 is 30 degrees. This is 120. From 30 degrees to 120 degrees is 90 degrees. So we have a 3, 4, 5 right triangle. So that distance is 5. And it's a distance, so it's an absolute value. It's 5 units. There's no positive, negative, like issues going on here with this. Well, these are 2 very nice, clean, happy examples where the triangles that we could box in to help us find that D are right triangles. Well, what if they're not right triangles? What would we do? Oop, wrong page. I don't know why that's in there. And so here we have 3 pi over 2. So that's right here. We have 4 pi over 3. That's right here. And that's the distance we're looking for right there. So what we're going to do is go this way and this way. That's 4. That's 3. Okay, pi over 3 is 60 degrees. Pi over 2 is 90 degrees. So that angle right in there must be 30 degrees. So pulling that triangle out to get rid of the extra stuff we don't want to see, that's 30, that's 3, this is 4, there's D. So this is a place where we could use law of cosines. This is a side angle side. That's one of the conditions we use law of cosines for, and we can set it up to solve for angle or for side D. So it would be D squared is equal to 3 squared plus 4 squared minus 2 times 3 times 4 cosine of 30. Solve that equation for D, and that'll give us that distance. I'm not going through those steps in the interest of time. It turns out that that is root 13. It's an exact distance between those 2 points. All right, one more example of that type. 3 pi, that is right here. 3 pi over 3, that is right here. It's asking us to find that distance from that point to this point. So we know that length is 3. That length is 3. Pi over 3 is 60 degrees. Pi is 180 degrees. From 60 to 180 is 120. So again, we could use law of cosines in order to find that missing side D. There's a side angle side, set up law of cosines to get D. Now sometimes there's other options you could do. You could get a little bit more creative, like in this case right here. If you wanted to, that's 3, that's 3. You could drop in an altitude because the triangle's isosceles. It'll break it up into 60, 60. That'll be 30, 30. You can work off of 2 30, 60, 90s and do stuff like that. That's always an option. Once you find the triangle that models the distance you're looking for, there are usually multiple things you could do in order to get that distance. The 2 quickest, easiest, not really looking for any shortcuts, law of cosines, or like we did with this here, or these here. Sometimes you could identify it just as being a straight upright triangle, and there's like no trickery thinking outside the box, just a squared plus b squared equals c squared. All right, that will wrap it up for what we need to know for day 1 of polar coordinates, which again is in the 10.6 to 10.8 part of your textbook.